In this video, we're going to be talking about Unit 2 Notes 4, the families of elements in the periodic table. But before we get into that, there's a couple of things I'd like for you to know. In the Unit 2 module under Notes 3, where it says periodic table, there's a couple of things I'd like for you to note here. There's this guy right here, the periodic table color sheet, the color in sheet. I would like for you to either have a digital version of this or a physical version of this, doesn't matter, as long as you can keep track of it, and fill it in as we move through this entire unit. By the end of this unit, this entire periodic table should be colored and filled in. It looks like this, and so it's completely blank of void of color, but so it's just a black and white periodic table, but it does have the different groups that we are going to cover with a certain, it's basically waiting for a color to be filled in. So we're going to cover a lot of these groups today. And you're basically just going to cover these in. The other thing I would like for you to note on this periodic table is the valence electron pattern that we talked about last class. And if we pull up a PowerPoint, this is the pattern that we talked about, where we have the valence electron pattern 1, 2, 3, 4, 5, 6, 7, 8. Just making sure that whatever color you choose to write down the font of these numbers is the same color of this font where you write down the word valence electron pattern. There will be one more pattern that we write on top of that, and so that's how we're going to distinguish which pattern is which. There's the valence electron pattern, and then later on there will be also the ionic pattern, but that's not going to be until Unit 3. The other thing I'd like for you to know in this module is this document right up here, the elements you should know. Okay, so if I go ahead and open that, this is basically a list of all the elements that you should know. What I mean by that is you should know the symbol of that, because we're going to be referencing these elements pretty often. And just by using the periodic table for a long time, you're going to be able to just memorize these. It's going to become second nature to you. You're just going to learn it as we go along. But a lot of them you might not see very often, and so it's good to memorize all of these symbols. And there is going to be a quiz based off of this called the Element Symbol Mastery Quiz. And so for my classes, you'll be taking this quiz, and you can take this as many times as you'd like, but just know that every time you take it, you're going to get a whole new sample of 7 different elements coming from this list right here. You'll also notice that on this list of elements you should know, there are several that are highlighted. These are just elements where the symbol might be a little tricky, or it might not necessarily make sense, like Na for sodium or K for potassium. Those are just kind of tricky ones, and those are because those elements have a name that has a different root. Like for instance, sodium in Latin is called natrium, hence why it's Na for natrium. But the other ones should make sense, like lithium is Li, calcium is Ca, so on and so forth. So the other ones are just abbreviations of the word itself. And again, these are ones that you should know. Study them for a little bit, maybe even make some flashcards so that you can know them. And then we'll be taking this quiz later, the Element Symbol Mastery Quiz. But without further ado, we're going to go ahead and jump right into the notes. So if you want to pull up the PDF for the notes, we will go ahead and begin. Just as a review from last time, we did mention in the periodic table that over 2/3 of the elements are metals. So you can see that all the gray elements here, those are metals, and then we have non-metals, and metalloids are going to be the blue ones that have properties of both metals and non-metals. So what we're going to do today is talk specifically about the metals. Okay? So some properties of metals that we want to understand. We know that almost all metals have luster, they have thermal conductivity, and they have electrical conductivity. So what does that mean? Luster means that it has some kind of reflective property, that it can shine and that it could reflect light pretty well. Some metals do it better than others, and some metals actually rust or oxidize very quickly, so that luster actually loses its appeal very quickly. Like aluminum, for instance. Aluminum is metallic looking, but it doesn't really shine like a mirror does, and that's because if you cut aluminum, the raw aluminum just reacts with the oxygen that's in the atmosphere, forming this almost protective oxide layer. But other metals like chrome, or chromium rather, and something like gold or silver or titanium, they can be polished to have a lot of shine to them. So a lot of metals do have luster. Metals also have thermal conductivity, meaning they are pretty good at transferring heat from one source and throughout the entire sample of metals. So metals are really good at thermal conductivity. Some metals are better than others. Referencing aluminum again. So you can see here we've got Pots and pans, probably either made out of aluminum, maybe steel. Sometimes you can have like cast iron pots and pans, but they're typically going to be made out of metal. And different types of metal will conduct heat differently, and they will actually cook differently. So if you're planning to go into the culinary world, you got to know things like that. You got to know that certain metals will cook foods differently. And then finally, electrical conductivity. If you want to go into electricity or electrical engineering in the future, you have to understand the properties of different metals and how they conduct electricity really well. For instance, for a really, really long time, we used aluminum wires instead of copper wires in our homes. This is a long time ago. But we stopped using aluminum as the standard for wire because when aluminum oxide, what we talked about earlier, when aluminum mixes with oxygen in the air, when there's too much electricity going through that, it can actually catch on fire. And so, 100 years ago, when we had early forms of electricity, people weren't running large appliances and TVs and stereos and charging their laptops and running their computers and things like that. They didn't have those things, so they weren't running that much electricity. But nowadays, we have all these different appliances, and if we try to run those appliances through the aluminum wires, they can actually overheat and cause fire. So nowadays, we have copper as the main metal to conduct electricity. Does that mean copper is the best at conducting electricity? No, definitely not. There are metals that can conduct electricity way better than copper. For instance, gold. If you take like a memory card or like an SD card like this, it actually has gold plates on it. That is real gold. It is not a significant amount to actually, be expensive. But why do we use gold on things like that rather than copper? It's because it conducts electricity really well and it can actually transfer data very, very fast. Why don't we use gold wires in our homes, in our buildings? So why don't we just run all electrical wires with gold? Well, that can add up. That's a cost. That costs a lot of money. Gold is expensive. So copper is significantly cheaper, and that's why we use copper wires instead of gold wires. All right, just another example of how we can show different types of luster and thermal conductivity and electrical conductivity. So again, luster, it can be appealing for a lot of different reasons. Chrome rims or certain parts for instruments is like a bridge to an electric guitar. And then we talked about thermal conductivity. Hard anodized aluminum pots are really good at conducting heat evenly, and they actually cool down much faster than stainless steel pots. Stainless steel is pretty common because it's easy to maintain and wash. If you've ever used aluminum pots, they're really great to use if you know how to use them properly. You have to use lower heat and season it properly, just because the food can get stuck to it a lot easier. And then finally, electrical conductivity. Most headphones, like cheap headphones, have the wired ones, not Bluetooth ones, but wired ones have a silver plug. It's not really silver. It's more like zinc and nickel-plated stuff. But really high-end headphones have gold connectors because, again, gold is a really good conductor of electricity and can actually transfer data much better. Moving forward, metals have this kind of structure where they have protons stacked like this and then electrons floating around them. And these protons actually form this crystal lattice structure where they form various patterns depending on the type of material, the type of metal. And so almost all metals are going to end up being solid. There's actually only one metal that is liquid at room temperature, and that is mercury, which is a very toxic metal. Every other metal is going to be solid at room temperature, but they do have various melting temperatures. Like, for instance, aluminum has a pretty low melting temperature in comparison to cast iron or brass or things like that. There's one metal, gallium, that can actually melt in your hand, which is actually kind of weird to hold because if your hand is warm enough, this hard sample of metal can actually melt, turn into liquid, and it melts onto, let's say you pour it onto a table, it'll actually solidify back onto that table. So gallium's kind of an interesting metal. But because they have this structure that we saw earlier, this crystalline solid structure, the protons are going to be stacked way more uniformly instead of flowing freely. And that's why almost all metals are going to be solid. All right, so we're going to actually jump into talking about the different types of metals and their certain properties. And so this is where we actually want to start filling in that periodic table PDF that I mentioned earlier. And the first family that we're going to talk about is the alkali metals. And the alkali metals are going to be in group 1A, way up here. And notice I did not highlight this one because typically hydrogen is not considered to be part of that family. Hydrogen is a gas. There are instances in which we've done experiments where hydrogen has metallic properties, but for the most part, hydrogen is not regarded as a metal. Okay, so we're only talking from here going down: lithium, sodium, potassium, cesium. All of those are going to be the alkali metals. Since they are in group 1A, how many valence electrons do they have? They have one valence electron. Okay, so this is what that looks like. If I were to just draw a simple Bohr model of the atom, which is technically an incorrect model, but that's okay, we can see that they all have one valence electron. This is lithium, so this is the 1s2 orbital, s2 meaning that there's 2 electrons, and then this is the 2s orbital, and there's only 1 electron there. Sodium's energy levels, this is the first energy level right here, and this is the second energy level. So we have 1s2, and then 2s2 and 2p6 form 8 electrons, and then 3s2, or 3s1 rather, that's the ending for sodium, so that's where that one valence electron is. So the one thing they have in common, once again, is that they all have one valence electron. And that actually makes them pretty reactive elements. These metals are fairly reactive because they want to have that full ring on the outside. Both lithium and sodium, they want to have a full ring on the outside, but they have like this one extra electron that's just kind of hanging out. They are very much willing to donate or get rid of that electron. So let's take a look at the sodium really quick. Sodium wants to have a full ring on the outside so that it can kind of remain comfortable and kind of be a stable atom, but it has this one floating electron on the outside. So it's very much willing to donate that electron to another thing. When we start talking about reactions next unit, sodium can donate that electron so that it has a full ring on the outside. Okay. In terms of reactivity, they are all very reactive, like I mentioned before. Lithium is probably going to be the safest, and then francium is going to be the most dangerous by far. Francium is so reactive that we can't really contain it for more than a couple of minutes before it starts reacting with things. Lithium, you've probably heard of instances of like lithium batteries catching on fire. You should never pierce a lithium battery because it'll start reacting with the things in the air like oxygen, and it'll start catching on fire. So it's very reactive. And I actually have a video of how reactive these metals are when you mix them with water. So let's go ahead and take a look at that video now.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen, but this time corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
All right, so I realize that video is a little low quality, but hopefully it gets the message across about the reactivity of the alkaline metals and just how reactive they are. Because they are so reactive, especially with water, they can react with the water that is in air. So they are kept typically in like mineral oil so that they don't react. They don't react with the mineral oil, so that's why the mineral oil kind of protects the metal from reacting with anything. And that's how we properly store a lot of these metals is in mineral oil. All right, so the first practice problem in our notes is research why do we need sodium and potassium in our diet. This is kind of like an important mechanism that we'll learn about in biology next year. So maybe do like a minute or two of research and try to figure out why do we need sodium and potassium in our diets. All right, so if you did research why we need sodium and potassium in our diets, it's because in sodium and potassium, and they are kind of like these things called ions in our body or electrolytes. You might have heard of this term before. And electrolytes are used for cellular communication, but also for muscle movement. So we need sodium and potassium both for muscle movement, and that's why we find high levels of sodium and potassium in things like Gatorade and Powerade, where we can replenish those electrolytes. All right, so that's why we need sodium and potassium. The next group of elements are called the alkaline earth metals, and the alkaline earth metals are in group 2 of the periodic table. You can see right here that is the second group, and because they're in group 2, they have 2 valence electrons, right? And so taking a look at 2 examples, we have beryllium, which is the first one. It ends with a 2s2, so it has 2 valence electrons on the outside, and then magnesium, which is kind of like a larger one, has 2 valence electrons on the outside. Similar to the alkaline metals, if they want to be kind of like in their comfort state or when they're reacting with something, what they are very willing to do is donate those 2 electrons on the outside. So magnesium, if it wants to have this ring be its outer ring so that it's completely full, this electron and this electron would donate to something that would need those 2 electrons. So they're a little bit more stable than the alkali metals. They don't need to be stored in like mineral oil or anything, but they can still be pretty reactive. Okay. In raw form, we can hold them, and they just look like typical metals, but they do react if you provide enough energy for them. So, if, like for instance, if we light them on fire, they burn at very high temperatures and very bright colors. They catch on fire pretty easily, which is kind of weird to think about with metals. Like if you throw metal in fire, it typically just heats up, but the alkaline earth metals actually do catch on fire and they react. And when they do burn, they produce bright colors. And that's why we use them a lot in fireworks. Okay, where do we also find alkaline earth metals? A lot of them are very important, and this group contains the most abundant metal in our bodies. A lot of times if I ask students, what do you think is the most abundant metal in our body, the common answer that I get is iron, because you have iron in your blood. While that's a good answer, that's actually not the correct answer. The most abundant element in our body is calcium. Calcium is a metal, and we have calcium in our cells for it's another electrolyte, like I mentioned before, like sodium and potassium. We also have calcium in our bones and our teeth as well, so it makes it the most abundant metal in our body. Okay, moving forward, we're going to skip over to the short section of the periodic table, and that's going to be the transition metals. So go ahead and color that in as well on your periodic table. The transition metal is that entire middle section of the periodic table, the short section. Those transition metals are going to be found in groups 3 through 12. A lot of times periodic tables will call those like the B columns because they're like a subset, they're shorter. These are ones that when we think of the term metal and something having metallic properties, these are the ones that we're going to be thinking of a lot of the times. Transition metals occur commonly in nature as pure elements. We can find them sometimes like mixed in with rocks and things like that, and we just kind of have to break them apart to free up the metal. So like for instance here in Minnesota, we have like the iron range where we can actually break apart a lot of the rock and extract iron from that in its raw form. So they do occur in nature pretty often. They are also responsible for the colors that are used in a lot of pigments. So when we talk about ink or pens, they contain a lot of the metals that are part of the transition metal family. So when we are talking about like these powders that we can use for paint mixing, here's just an example. These metals, these transition metals, are responsible for the different colors that we can see. Okay, they are also used a lot of times for like jewelry. For instance, gold, silver, titanium, and platinum. Those are going to be ones that we see a lot of times in jewelry. Sometimes copper as well. It can be used in that. And so what we can discuss is that when we mix a lot of these metals together, we can actually form different things called alloys that can help strengthen the properties of the transition metals. And we use them for jewelry. Sometimes we use them for plumbing or for instruments, things like that. And a great example of that is brass. Brass is a mixture of copper and zinc. Copper itself is a pretty weak metal. You can take like a sample of copper and just like bend it pretty easily, like a copper wire. You can just bend it back and forth, just like a paper clip. And copper is pretty weak, but when you mix it with zinc, it makes it extremely hard to break and very resistant to rust. Copper rusts pretty easily. If you think about like the Statue of Liberty is pretty much entirely made out of copper, that green section. But the reason why it's green is because the outer coating of the copper mixed with the seawater in the air that's kind of evaporated, and it caused it to rust and created this green outer coating on the outside of the Statue of Liberty. So copper can rust pretty easily, but when you mix it with zinc, brass doesn't rust that well. And so when we mix these two metals together, I think I mentioned the term, it's called an alloy. So many transition metals are made into alloys in order to combine their properties. So copper and zinc, great example of an alloy. Here is an example of copper in its raw form. Sometimes we have it in copper shavings in the laboratory setting. A lot of times we have copper as wire. And then here's samples of zinc that you can find. And a lot of times you can just get samples like this for laboratory settings as well. But when we mix these two together, we melt it and then pour it into like a mold, we can form brass. And brass is, again, very resistant to rusting, and it's a very hard metal, and that's why we use it for a lot of plumbing fixtures and for brass instruments. So brass, just to clarify, is not an element on the periodic table. Alloys themselves are not elements. Alloys are mixtures of elements that are used to kind of strengthen them and to combine both properties of those elements. All right, here's another example. The purity of gold is determined by the different ratios of gold, copper, and silver present. So Bruno Mars a couple of years ago made it very famous, the status symbol of having 24 karat gold. That's not necessarily beneficial for the modern middle class family that wants to get like wedding rings or something like that. 24 karat gold is very shiny and it looks nice, but is it extremely soft a sample of gold? The gold is not as a strong metal. It's similar to copper in the sense that it is soft and it's bendable. And if you have like a wedding ring made of 24 karat gold, you probably can't be in a work area where you're using your hands a lot because you're going to be denting and scratching that ring a lot. Maybe it might be good for like a necklace or for earrings, 24 karat gold. 18 karat is very high value gold as well. It's a very, it looks pretty much just like 24 karat gold, except it's much stronger because now we've combined the properties of copper and silver, and it makes it really, really strong. 14 karat gold can also be very strong, but to the trained eye, like a jeweler, they can probably tell the difference between like 14 and 18 karat gold, and probably even also 18 and 24 karat. But modern people, the common person cannot tell the difference between 14 and 18 karat gold. You are adding a little bit of copper in there, so it might appear to be a little bit on the darker side versus 24 karat gold, which is closer to the lighter color. But it is significantly stronger and cheaper because copper is a cheaper metal. So here's an example of just pictures of jewelry showing you the differences in the carat of gold, which is, again, the percentage of gold. We got 18, 14, and 10. Maybe to the untrained eye, you can kind of figure it out, but if you're just getting a quick glance, people are not going to be staring at your jewelry, your wedding ring, and just like analyzing it to see what the carat is. I can tell from this picture that 18 karat gold is slightly brighter, just because it has more gold. The 14 and the 10 look most similar to one another. So 10 karat gold has even more copper. It's like more than 50% copper and silver. There's more copper and silver in here than there is actual gold. All right, 24 karat gold is the highest carat value. It's the amount of weight of gold, and you can't go above 24 karat gold. So that just means it's 100%. All right. One last example of an alloy is steel. Steel was a great invention for people that made weapons or wanted to make strong things like nails or basically anything made out of iron. If a long time ago people were making swords, for instance, and they were using iron that was dug out of the mountains, and what they would do is called smelting. They would take the iron and they would smelt it, form it into a long piece of metal, and then kind of heat it up in a fire, and then hit it with a hammer and anvil until it formed a really sharp edge, and then that's how they would make a sword. But what they also noticed is that if they took that iron and dipped it into the ashes of the fire, the ashes contained a lot of carbon, and the carbon would actually embed itself in the gaps of the steel. So in this picture, we've got iron and we've got carbon being our two elements, and iron can be found here. And when you stack them together, you can see kind of like these gaps that form. And remember, this is like a three-dimensional view. So if you took like a whole bunch of like basketballs and you stuck them into a pyramid, there's going to be clear gaps in between the basketballs. But then if you fill those gaps with like tennis balls or so, I don't know what you could fit in those gaps, maybe golf balls. Basically, what you're doing is you're solidifying that structure and you're making it significantly stronger. And so iron is pretty weak. It also rusts really easily, but steel doesn't really rust as well as iron. It can still rust, but it's significantly stronger than just iron, just by adding the carbon molecules in between the iron molecules. Finally, part of the transition metal family are called the inner transition metals. These are going to be the very bottom two rows of the periodic table. We've got what's called the lanthanide series, which is the first row, and then the actinide series. These are going to be on the very, very bottom. They're kind of that separate portion that's been removed from the periodic table. And they belong in periods 6 and 7 of the periodic table. These are going to be kind of interesting. They're all solid. A lot of them are laboratory made. They are not naturally occurring on this planet. So let me pull these notes up. They are very rare elements. Most of them are radioactive and or man-made elements, especially after uranium, including uranium itself. So taking a look back at here, uranium is right here. And so anything after here, a lot of these were man-made and a lot of them are radioactive as well. We don't really use these for a whole lot of things. We use them sometimes for radioactive sources like radiation therapy, nuclear weapons, or sometimes we use it for nuclear power. But a lot of these, most of the time, we're not going to be encountering them. Some of them, actually, I think it's americium. Let me find that one right here, AM. That one can actually be found in smoke detectors in our homes. So we use a small radioactive particle in our smoke detectors to detect smoke. It's not like a very dangerous radioactive sample, so it's not going to harm you or anything, but it is a radioactive element. So go ahead and take about a minute to 2 minutes to complete practice problems 2, 3, and 4, which are multiple choice questions. Go ahead and pause the video now and then work on those problems. All right, let's go ahead and start with practice problem number 2, which says this. Each element in an element family shares the same what? Average atomic mass, number of protons, number of valence electrons, or atomic number. The correct answer for this problem is C, number of valence electrons. So just remember, valence electrons can be determined by what number the column is for the tall columns. So every family has the same column, so they're going to have the same valence electrons. 3 says elements in an element family have similar what? They have similar atomic symbols, atomic sizes, atomic weights, or chemical properties. The correct answer for problem 3 is chemical properties. And finally, number 4, how do you know that potassium, an alkali metal, is highly reactive? It is because it conducts heat, it conducts electricity, it is a soft and shiny metal, or it has one valence electron. Just like we talked about before, the reactivity of an element is pretty much determined by its shape and its number of valence electrons. So answer choice D is correct here. All right, so that concludes Unit 2, Notes 4 on the metals of the periodic table.